Hi, this is Geometric Random Variables. In the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that this is the only way a player could get out of jail. On each roll, the probability of rolling doubles is 1/6. Find the probability it takes 3 turns to roll doubles. So this means that a person would not roll doubles twice in a row, and the probability of each of those is 5/6. And then they roll doubles on the third roll, which is 1/6. So not roll doubles, didn't roll doubles, and then roll doubles the third time. So we have 5/6 times 5/6 times 1/6, or 5/6 squared times 1/6. This ends up being about 11.6%. How about the probability it takes 5 turns to roll doubles? So that means a person did not roll doubles 4 times in a row and then rolled doubles. So 5/6 to the fourth and then times 1/6. So about an 8% chance of that happening. So this is basically just, it's called a geometric random variable, where we have a fixed probability of a success happening, and then we're finding the probability that it takes a certain number of trials until we get a success. If P is the probability of getting a success, then the probability it takes K trials until your first success is 1 minus P, because this means you didn't get a success, to the K minus 1, and then you got a success on the Kth trial. So like in this case, in the previous case, on the 5th trial, so we had 4 failures, and then we had on the 5th trial we got a success. This information is on page 404 to 408. So the definition of a geometric setting, so when we would use this situation, is it says a geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of successes must be the same. So this is really similar to binomial. In fact, let's talk about what makes this different from binomial. So in binomial, we check these 4 things to know that it's a binomial setting. We use bins for it, and B stood for binary. And in this case, it's still the same. We still have a probability of a success happening and then a failure. It's just kind of like yes or no outcome. We're still looking for independence, that the each trial is, or each trial is independent from the previous one. But we don't have a fixed number of trials. We're just trying and trying until we get a success. And that's what's different than binomial. We still have S, which is success, or the same probability for each success. And that stays the same each time, so we're still looking for that. So basically just BIS instead of bins. We don't need the N for it to be geometric. And the formula, which is what we were just looking at on the previous slide, basically you have the probability that you did not get that success a certain number of times and then you got it on the last time. This is how it looks on the formula sheet. So you have your formula, and then we also have the mean of a geometric distribution and then the standard deviation of a geometric distribution. So let's look at those for the previous example. The mean for the number of times it takes until you roll doubles would be 1 over P, and P in this case was 1/6, so 1 over 1/6, we just get 6. And what that means is if we tried to roll doubles many times, we would expect it to take about 6 tries until we got our first doubles on average. The standard deviation is the square root of 1 minus P over P. So in this situation, it would just be square root of 1 minus 1/6 over 1/6. We get 5.477. And that means if we tried to roll doubles many times, we would expect each try to vary from the mean of 6 tries by about 5.477 tries. Let's try another one. Find the probability it takes at least 7 turns to roll doubles. So let's just say X is the number of tries until a success. We're looking for the probability that X is at least 7, greater than or equal to 7. This means that it took 7 tries to roll doubles, or 8 tries to roll doubles, or 9 or 10 or 11, all the way to infinity. It could just theoretically keep going. So we can't really calculate those one at a time and add them up. What we can do instead, and this is what it would look like, by the way, if we tried that. So this would be 6 not doubles, 6 failures, times we got a success. We got doubles on the 7th try. This would be 7 failures, and then the 8th one was a success, and so on. What we're going to do instead is the complement. So we want to do the probability of getting doubles on the first or second or third or fourth or fifth or sixth try, and then just do the complement of that. So the nice thing is we can actually use the calculator, and there's a geometric PDF and a CDF. So I'm going to show you that. We go to second distribution, and I think it's all the way at the bottom. Okay, so PDF is if we just wanted one trial. So let's say we wanted it to happen exactly on the 7th try. Our probability was 1/6, and we want to get a success, let's say, on the 7th one. So this would be, PDF is when you just want that exact number. We want it on the 7th try exactly. We can use CDF for anything up to that number. So let's see, we wanted up to 6, and then we're going to do the complement of that. So if we put 6 in, that's going to be the probability that we get a success either on the first, second, third, fourth, fifth, or sixth roll. So I'm going to do the probability. And if I put 6, since I'm using CDF, CDF means cumulative, the C is cumulative, that means this will give me the probability of either the first, second, third, fourth, or fifth, or sixth roll. And then we actually want 7 or more, that it was on the 7th or 8th or 9th or 10th, so we're going to do the complement. And then that's our answer.